Hello, everyone. We're Group 54, and our project is Smart Ergonomic Adaptive Technology, also short for SEAT. Our advisors are Professors Milton Diaz, Kamran Sarohi, and Dr. Sasan Agani, and our members are Shashank, Pranav, Christopher, and Aryan.
So currently, poor posture has created a large increase in musculoskeletal conditions and issues, and a lot of the current issues on the market are not dynamic enough for to adjust to varying user postures, and they're also very expensive. So our solution looks to create a smart system that adjusts postures and classifies them as well.
So our proposed framework for solving this problem is a pipeline of sensors to motor control. So we initially start with pressure sensors that are spread throughout the seat, and then that collects data, which is sent or collects data using the Arduino, which is then sent using serial communication to a host PC. That host PC then connects both to a web app and an ML model. The ML model classifies different postures based on the sensor information, while the web app allows for user metrics as well as different trends and live pressure sensor mapping. Then the ML model is then connected to back to the Arduino, which sends motor controls to the motors on different parts of the chair. So the benefits to the industry is that our product improves individuals' postures without an invasive manner. So there's no actual like grabbing and adjusting. It's more like adjustments in a term of the back positions to adjust for new to maintain a neutral position with the spine, allowing for good posture and preventing any musculoskeletal issues and any chronic back pain. So it's also inexpensive. The other like different chairs and ergonomic chairs are upwards $1,000 or even more, depending on the different techniques they use to adjust for posture. Ours maintains all of those same functionalities while being within the $300 to $400 range, as well as more functionalities as well. And again, because it's cheap, that allows it to be used in any location, school, workplaces, homes, etc., allowing for anyone to access it, big or small.
So for the design, we chose to create a back structure made of wood to hold up the motors and push the pads. And we have four motors on the top, two motors on the top, and then two motors on the bottom to control the upper lower parts of the padding. And in the front, we have underneath the pads, we have sensors, and we cover those sensors with pads to create a more comfortable chair.
So our project is split in three portions, the hardware piece, the ML piece, and the UI piece. As for the ML piece, this is responsible for detecting a user's current posture. We wanted to experiment between two different type of classifier models, SVM, support vector machine, and random forest. After some thorough experimentation, we found that random forest yielded better results. And this architecture is basically just a bunch of decision trees that make multiple predictions, and all these predictions are combined to produce one big accurate result. So what we do is we collect our pressure sensor data to assess a user's weight distribution and arrange this into a vector as shown here with all 10 values. Uh, this vector is then input into our model, which we can then use to output one of seven different cases, six of which are six different postures, and one is just a null case, indicating that no one is currently sitting in the chair.
So our user analytics position, which is then taken from both the ML model and the sensor data, is we're able to see live pressure mapping, which is when a user sits on the chair, we can see where their weight is distributed accordingly, back and seat. It also lets you know based on that what their current posture is, whether it's upright, leaning forward, etc. It also has posture trend graphs that's over time, so you can see like whether your posture has been improving or reducing, as well as a score that tells you whether it's been good or bad. You're also able to configure your chair based on different positions, allowing for a better accurate reading for when you sit on it as it adds to the consistent growing ML model that we have.
So this is just over like project execution of how we built everything. So the image on the left shows how we arranged our sensors, varying sensitivities. That we have four sensors in the back region and six on the seat region. Uh, this basically lets us get a good reading of the weight distribution of an individual currently sitting in the chair, like depending on what angle they're leaning in or how they're slouching or however they decide to sit. On the right, you can see two images. The first one shows our motor driver setup, how we set up each motor. These are DC motors, so unlike servo motors, we can't control the exact angle. So we use H bridges to control the spin, duration, and direction of how these motors actually spin and allow us to adjust different regions of the back. And finally, we also have our main circuit down below showing how we set up just a bunch of voltage dividers with a main Arduino so that we can read all the values from our sensors accordingly.
So for the CAD models that we built, we had on the left and right, we had plates. The left plate is for the lower back, and then the right plate is for the upper back. And then we also have motor gear parts. The motors are rotating, so we needed a linear movement from it. So we created gears to create a linear movement for the pushing of the pads.
Yeah, so currently we've only trained on six different positions. Obviously, this can grow as we have more data and we train it for different positions, but for testing purposes, we only have the six. These include the ones that are shown on the screen: upright with back support, upright with no back support, leaning left, leaning forward, leaning right, and slouching.
And now we're just going to show a quick video of how it works. So here you can see me sitting in like the slouching or leaning back position. And what's happening here is that our model is getting real-time data from the sensors and it's detecting that I'm leaning backward. So it's consistently predicted here. As you can see, the bottom motor kind of pushes the lower back region, forcing me to sit a bit more upright. And then the upper two motors come in to support me a bit more. Obviously, right now, this still needs a bit more touching up. But as you can see, the motors move into place to allow me to sit in a more ergonomic position. And we'll be fine tuning how much each motor adjusts to depending on what posture you're in. So these are some results of like just I guess graphs to show how our progress has been made so far. This is for our random forest model and how it's been performing over like the different periods of time. So the first graph just shows with the number of trees that we used in our random forest model, how it improves. And we saw a peak performance of around like 200 decision trees. So we kept it around that. Uh, the second curve, or learning curve, shows how with an increased data set, we yield better and better accuracy. So right now we have about data from about like 20 people, which yields about like 16,000 vectors to use. We'll be expanding this data set as we go on. Down on the bottom left is a graph just showing how important different sensors are in assessing the individual's weight distribution. And finally, we also have a confusion matrix just showing how accurate the model is with response to like how I guess confident is in identifying a specific posture and if it confuses it with any other postures. Right now, we have trouble differentiating between leaning forward and sitting upright with no support as it's triggering the similar sensors. So we're working on just improving that part, but otherwise, it's still pretty accurate in terms of distinguishing between all six postures.
So for cost of manufacturing, the chart on the right shows the prices of all the uh, items that we've bought for this current project. And for a mass production estimate, we expect that the volume, we would have a volume discount on bulk purchasing for electrical components such as the sensors, H-bridge, and resistors. And currently, it's run on a local host machine, the model and the web app, and we hope to make use of a Raspberry Pi so everything is on the system, and we don't need a computer anymore. So that would be an estimated cost of $99. And we would also want to host the web app on a cloud server. So we expect that to increase the cost as well. And we estimate that the mass production cost would most likely reach about $450 per unit.
And yeah, just a special thank you to our advisors and their constant guidance and support throughout this process. And also thank you to our peers and other students that helped us with collecting data for our ML model. Uh, Thank you all for listening. Have a great day.